And please, I don't know, did you get the email?
Yeah.
Everybody? So the circular email works well?
I got it.
Yeah.
I rarely look at it.
Okay, I can send another email then. Okay, today we are going to start a new topic, a new chapter. This chapter is the one that we are going to work with both internal and external forces. So what happens in real life, we load things with external forces. And this is going to create a deflection in the material, whatever in the material, that is internal forces inside it. Just like I'm carrying, you have supposed to carry it like this for a few minutes, what happens? So this is external load. This external is going to put me to work internal load in here. So when we deal with this stuff, we are going to deal with both. We cannot ignore one without another, okay? So we are going to deal with internal forces, external forces. This topic is about the trusses. And these trusses, when we deal with the truss is the most economical solution for wide areas. When you look at bridges, truss, 200 feet, 300 feet, you can put a truss. Okay? So the truss comes in general like the roof, your roof. This is a simple truss. Okay? These trusses, they have some rules to deal with them. In order to consider them truss, and for you and I to work with them correctly, here are the rules. If you go on your roof and you walk there, you could stand right in here. Agree? However, we don't apply the loads in the middle. So all loads are applied at the joints. That's the very first rule you need to remember. What we do. So here is the roof. From the top you look at the roof. You have these 2x6s, 2x12s, whatever you have. So I come here in the middle, to the middle, and I say this area is carried by this guy here. Agree? And so on. And from here to half of this area is carried by this one, and so on. And I divide it. You will learn later on in next year when you go to Portland State about when you get to design classes and stuff like that, how to divide the load and apply. So the very first thing is the loads on the truss are applied on the joints. The second thing, all members are straight members. Even when you look at the Halton Bridge, this is not art. Because something like that, I consider this is a straight member, this is a straight member. All members are straight. All members are limited joint to joint. And people look at you, what the hell is this? So this is not one 200 feet element. This is, let's add a couple more here. So I look at it, one element here, one element here, one element here, one element here. Even if you go underneath the Halton Bridge, you will see a member like this, continuous. We study it like it is separate from one joint to one joint. Is this clear? in order for us to deal with this kind of structure, we have two methods to look at it. The first one is called method of joint. The method of joint, you learned it earlier in chapter 2. We used to do what? We used to do what? We have this cable carrying this part in here. What we used to do? Look at it as a particle, correct? What does that mean to your brain? We came here and we cut this circle. And we say we have this force here, we have this force here, we have this W here, sum of forces X, sum of forces Y, or triangle force, so, correct? What I did in here, I isolated the knot where the cables connect. In this case, I will isolate the joints. So, here is a joint. Here is a joint here. 1, 2, 3, 4, and 4. And you can see this is. Then, next week, we will go to method of section. Method of section in which I come closer and say, everything from here, this is an element, here is a vector. This is the element, here is a vector. This is the element. Any element that I cut, I replace it with a vector. My advice to you, generally, we try to, when we do this section, to create or maximum 3 elements, correct? Because we have 3 equations, sum of force in X, sum of force in Y, and sum of the moment. So don't go cut anything like here I have 4. When we do the section, we try to go with the 3. Questions about this part of chapter 6, sorry. If you find my glasses, let me know. Where I go. Chapter chapter 6. Please open your book to page 286. 286. And look at these structures, trusses, different kinds of trusses. Spacer truss is a combination of straight, simple trusses. We talked about the Houghton Bridge. So if you go to the north side, you will see this whatever. That's the north side. If you go to the south side, you will see same thing, correct? One south, one north. If you go from the bottom, look there. If you go ride the bridge from the top and look down, you will see such a thing. This is, we call it straight or simple. Each one of them is a straight truss or simple truss. When we put them together, we call it space truss or 3-dimension truss, whatever you like to call it. Okay? So here they call it simple truss. When we deal with method of joint, I need a piece of paper, and let me create very simple, just like let's call this as a truss. Simple one. This is connected here with a pin. Connected here with a ruler. These are on the same line. And we have one force here, 100 Newton. We have one force here, 200 Newton. Uh, 3, 5, 4. Find the internal forces in each element. So this is given. Find internal forces in each element. Indicate whether it is compression or tension. I forgot to talk about compression and tension, guys. Here's the pen. Any of you wants a pen? Anyone want? Yes. Tension. What is this element under what kind of forces? Compression. Correct? Compression. 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 Look. Look. A hole in here, correct? Did you see this hole? That because there is a force get inside my hand. So I put a compression, correct, on it. The reaction. What you see in here is the reactions. So how you can tell this is tension or compression? All the time, think about this. If you think all the time about this and see the impact on your hand, and I give you this pen to try because I'm nice. I don't want you to use your pencil. Okay? So, this is a simple truss. Let's call it A, B, C, D. A, B, C, D, E. Sometimes we don't need to calculate the reactions. Sometimes we should start calculate the reactions. The method of joints tells you to go start with the joint that has maximum 2 unknowns and move. So I can assume that this truss has this reaction here, EX only. Everybody agree on this direction?
Yes.
This one has this direction, AX. Agree on this, AX in this direction, and AY. How much is the value of AY? Come on, 300. Sum of forces on Y, I have only AY, and they have 200, 300. That's sometimes you need to push yourself to do things a little bit faster. Anyhow, so we can calculate AX and EX and AY and start from there. That's one option. The other option, we said you can isolate all the time, write it down when you deal with joints. All the time, you isolate one joint that maximum has two unknowns, maximum. Okay? Is this clear? Maximum, two unknowns. You can have a paper like this as well. Joint B, 1, 2, 3, 4.
Don't do that one.
And external force, but the external force is known, correct? I cannot start with it. Joint D, 1, 2, 3. Three unknowns, I cannot start with it. Here, 1, 2, 3. EX is still unknown. I cannot start with it. Here is one. Only one, three unknowns. So I need to calculate the reactions in order to deal with this one. Because this is one element, this is one, this is one. Three unknowns at this moment. C, it has one force here, it has two elements here. Can I start with C?
Yes.
Let's start with C. Do you know why I did this paper? And they have been doing it for 8 years. Because the students go finally and isolate a joint, and I don't know what elements they put there. So when I tell you just make a hole to see exactly what is there, you don't need to worry about it. Because this week, the end of the class, we are talking about zero element. The zero element is an element that we put it there to keep the structure on certain position. Is not supposed to carry any load. It's carrying load. But you go to a bridge and you find this element carrying 20,000 pounds. And this element carrying 200 pounds. We call it zero element. Just like you go, crane carrying in its cable 3 tons. And somebody comes to tell me, what's the weight of the cable? 300, negligible, we call it negligible, zero. So these are the zero element, when we deal with it, that makes the student confused because you have a truss like this, whatever, and they have a force in here. I am isolating this joint and the student looking at the force there. So I tell you, guys, just make a paper like this. I don't want to see anything more than what is in this hole. I don't care about the force, where is the force? I'm caring about that intersection only. Okay? Let's start. I will keep this statement here for other students. We have 3, 6, 10, 14, 26. We have 30 students so far in this room. Most of you are here. Maybe 1 or 2 are not aware of this statement. So the test next Monday, the 24th, will start at 6 to 7 o'clock to go home. Okay, let's start here. Leave it if somebody else comes. So, according to my paper, yes?
Just a quick question. The exam still on chapter 4 and 5, right?
4 and 5 only.
Okay.
Look, C, joint C. These two elements, CB, CD. Again, we need to assign direction for these forces. We don't know whether this is tension or compression, correct? So look at this. This element CD has only horizontal force. Agree? In order to be in equilibrium, has vertical. I should have from CB something to make equilibrium with that force. Agree?
Yeah.
So should be in this way. Can you see that? I want you to see that because it's easier for you later on. Look at CB has horizontal component pushing this way.
CD can go the opposite direction.
So CD should be the opposite way. Now, if you don't want to learn it fast, you don't want to help yourself, that's okay. Close eye and say, both of them are this way. I don't care. You will get a negative answer. The negative answer, the quantity of any vector, the magnitude is always positive. So what is the negative and positive? Opposite direction. So no worries. If I am trying to make your life easier, if you do this logic, you get direct answers. Why? Because what happened if I put it this opposite direction, I get negative. Before I step to the following joint, D for example, I need to change it because I need to carry that tension or compression from this joint because this is pushing towards D or pulling D, correct? So if I get a negative direction, I need to change it there, then come apply it in here. And this is what the students make mistake. They get the negative and they say, this vector is a 20 pound in this direction. Okay, move to the next joint. They don't move it correctly as it is. All we need to do is to apply two equations of equilibrium. That is simple. Method of joint, very simple. Sum of forces on X, sum of forces on Y. I will start with YX. I don't know CB. If I start with Y equals 0, what I get in here? I get CB, correct? In this case, I have negative 100, positive CB sine alpha. He says alpha is 30 degrees. I don't know that. Let's see.
26.
Alpha equal arctangent of 4 over 8. Give me alpha, please.
26.6.
26.6.
I was just guessing.
Everybody agrees on this? 4 over 8. From here, CB equal 100 over sine of 26.6. Give me a number.
223.
Yeah, 223.
223. Now, next step is sum of forces on X equals 0. I have CB is 223 cosine of the 26.6. This hitting this way is negative. Positive CD equals 0. What is CD, please?
It is 199.
499?
199.
199. Anybody else? I encourage you to come back here and you see this is here CD 223. This is here, CD 199. Look now to the next joint. Next joint D. D is this direction, opposite direction, 199. This here is this direction, 223. These arrows that I put here represent the reaction at the joint. So, if this is reaction at the joint, getting inside it, pushing inside the joint like this pin pushing inside my hand, then what is this element?
Compression.
This is tension.
Oh, isn't it the other way around?
No, if it's pulling away from it, it's tension. So if the arrow's going away from the joint, then it's pulling. All right.
These elements, these vectors again, these vectors here representing the impact on the joint. So here's the joint. Here's a joint. I put this. This is compression. What it does goes inside my hand. This goes inside the joint. That this is a compression. This one is pulling it. Agree? Okay. Which is the following joint now?
D.
D. Why D? Because here, D, it has two elements. I know the third.
Wait, I don't understand why the 199 is going this way at B. Why isn't it going the other way?
Okay. Do you have a rubber band?
Yes.
I don't carry rubber band.
Do you have a scissor? Do you have a knife? Hold it.
Never got
Hold it. If he has a knife there, if he now comes and cut it, what happens to the rubber band? It's going to hurt our fingers, both of
Yeah.
us. Correct?
Uh-huh.
Means the opposite directions.
Oh,
So
okay.
if I come here and cut this element, tension, correct? Here. Or getting back together. That's the difference between tension and compression. Does it make sense to everybody now?
Makes sense.
With the rubber band, but we didn't cut it? Okay. Let's go to C. Let's go to C.
You mean D?
D, sorry. D has 1, 2, 3. This one here is not. 199.
I'd say
This
we got another
CD is
199
gonna be
coming.
the opposite.
The other is ED, and this one is
B.
DB.
Okay.
So this is joint
Yeah.
D.
ED is gonna be 199.
And DB.
Let's look at directions first. What direction I should put for ED? This way, correct?
Right.
What about DB?
It doesn't matter.
It doesn't matter, he said. Let's start. Sum of person X or sum of person Y? Which one works here? Sum of person Y, sum of person X, because it's not doesn't make any difference in here. Sum of forces on X equals 0. I have ED is positive, negative 199 equals 0, or ED equal 199 Newton. Agree? Sum of forces on Y equals 0. I have DB equals 0.
It's on the
Zero force.
zero member.
There is no, we will talk about the zero force member later on. But here is a zero force member. We will learn why is zero force member. Again, we come here and we say this is 0. It's either or. Put a 0 on it like this, or just remove it from your free body diagram, because this is not element that carries the load. This is 199. What I should put here, in this direction. What I should put here,
199 in that direction.
some people don't believe me, and they want to calculate the external forces. The external forces, I will start here to say some of the moment at A equals 0. 200 times 3 is negative. 100 times 8 is negative, correct? And EX times 4 is positive, equals 0. From this, what is EX? 600 plus 800 over 4. 150 plus 250. What is that?
Hey, I got a question. 400.
No,
150 plus 250.
no,
50 plus 200.
no. This is not 199. Give me the number here.
400.
It's not 400.
350.
360.
Put it in your calculator, guys.
350.
600 and 800 over 4. 1400. Half of them is 7, half of the 7 is 350.
Yeah, because when you get some
Yeah,
X
you have-
force
yeah.
on.
I have another element here. If it was no element here, then yes.
Okay.
Okay, let's move on. Next one is this one. Or this one. Is it going to make any difference?
Guys, how come there's no load on D if there's a force going down on D?
On what? On E?
On D.
Why is it zero number?
No
Why is the y
element.
direction 0?
That is what I told you. That's why I made this paper
The
to the guys.
isolated-
This is the purpose of this paper. You guys visualize things that there's a force in here. This force is pushing through this element here. And Phi is telling me this is a 0. Because I look at this joint D only like this joint D. I don't care what force is there. Now at D, in order for D to be in equilibrium, I don't have any other force in Y direction, just this one. And some of forces in order to be in equilibrium should be 0. So this is 0. Make sense?
Clear as mud.
It doesn't make sense because you visualize the whole structure. But if you just cut this one here and look at it, there is no forces on Y, so this is 0. We will talk about it, 0 member, later on to talk. Which one do you want to go next? I can go to E, B, A. Any of them work.
You've already done lots of E by putting E
E.
in it.
Let's finish with E. Everybody knows about this test Monday. The last time, Monday, the test starts at 6, not 7. Joint E. Joint E, we have one here, we have one here, we have one here. We know that this is 199. I don't know this one. I didn't calculate this, sum of the moment. Okay? Let's assume that we didn't calculate sum of the moment. So this is supposed to be where?
Point to the right.
This way. This one this way. This is a 0 member. But again, just trying to convince you in different ways. This element is EX. This element here is EB. Correct? Sum forces on Y equals 0. This is gives you EB equals 0. Agree? Sum of forces on X equals 0. This gives you what? On X,
EX minus.
they have 199 negative, EX is positive, EB cosine beta equals 0 is negative. However, without fighting with
Yeah, we
E-
don't worry about that because EB is 0, right?
EB is 0, so I don't need to worry about this alpha, this beta. And in this case, EX equal 199, not the 350. Which one is correct now? What's that? It's 199, not the 350.
Maybe somebody calculated like CD wrong, and that's why we have 199 instead of 350.
Either one of the calculators, one of the numbers is wrong, or let's go to C, joint C. Alpha equal tangent negative 1/4/8. Again, alpha, guys, anybody else for alpha?
Yeah.
26.6?
What's your beta?
And CD is 223. Check these numbers here. Negative 100, positive CD sine alpha.
Yeah, that's right.
What did we get?
Okay, 223 cosine over 26 is
199.
What did we get for angle B?
200.
Yeah, we didn't plug in B.
200 times the 3, 100 times 8, CB times EX times 4. Okay.
What did we put in for the angle?
Yeah, we didn't subtract EB
For X.
cosine beta.
But it would be zero.
EB is 0.
Why
Right
does
above
it
it.
matter?
Why is EB 0?
Some
Well,
force
this
on
one-
Y.
Is there a question about this one?
Yeah.
This is a 0 number. Look, sum of forces on Y. This is on X, this is on X, this is the only force on Y component. Correct? Sum of forces on Y, let me write it down clearly.
0 number?
EB
Oh.
sine beta is negative, equals 0.
Same line of action.
There's no other force on Y. So this is 0 here. The EB here is 0. This is the AX getting 199. Okay, we don't need to worry about it. We'll move. And we'll see later on what we get. If this is 0 and this is 0, then what is this?
That'd be
Is it going to be 223?
Yeah, because it's in the same line
Let's
as the.
see. Let's see. If I go to joint B, joint B,
Oh, no, it's not because 200 is gonna,
joint B has this force here of 223, and we have a force here that I don't know, BE,
yeah, the 200 is going down, so that's gonna.
and we have here 0 and 0. If you want 0 here, 0 here, correct? I don't need to. And we have the 200 here. So these two zeros, I can get rid of them. Sum forces on X equals 0, 223 is positive cosine of alpha, negative BE cosine of alpha. That's all. Or BA equal to 23. opposite direction. Did you get that? Sum of forces on X. This has nothing to deal with X. The 200, correct? It's
Yeah,
vertical.
straight down. Why?
So this one, 223 cosine of 26, VA cosine of 26. Both of them are on alpha. BA is 223. Let's check our work at A. Let's check our work at A. A has AX, AY. And it has this one here, BA. This is joint B. So this is this way.
Yeah.
Agree? 223. Because this one is here, 223. Here, 223. This is joint A. Sum forces on X equals 0. 223 cosine alpha is positive, negative AX equals 0. What is AX, guys?
199.
How much?
199 again? Same as over here?
699 or
No,
what?
199.
199. Sum of forces on Y equals 0. I have AY is positive, negative 223 sine of alpha equals 0. What is AY? What is AY from this?
What is your sign?
99.9.
99.9.
That's what I've got.
100. Something, we are missing something in here.
Wouldn't it be that and the plus 200? Because the sine 220 from that joint,
You are looking at joint A. That's why what I'm telling you guys, you need this stuff in here.
oh, I'm looking at B. Oh, you're looking, okay, never mind.
In
No.
joint A, here, says joint A.
Okay.
Good.
never mind.
So, now let me tell you where is the wrong thing. Why we didn't get the right answer. This kind of structure, as it is in here, looks like we shouldn't have this as a symbol. This should be a pin. If it is a pin, then it's going to carry another load here. And in this case, this is not going to be 0, and the structure will carry its own stuff better. But again, this is just, I came up from some of these here. I looked at this, and I changed something. So that's all. But what we doing here? What's the point? The point is you isolate each joint separately, and then you isolate it. Apply two forces: sum of force on X, sum of force on Y. Look in your book for the questions and select a question to solve. Yes.
I thought we were supposed to start with the extensions and then go to the
It doesn't matter. You can do it if the structure is giving well. Yes, you can. We'll go to page 297, 296, 97, 98, and select one of these problems to be solved as method of joint.
Yeah, 15 no trust. 15.
I will start in this corner right in here. When you are done, which one?
15.
50?
1-5.
5? Everybody agrees on one